story is basically explaining what happens during synaptic transmission. So I'm going to be explaining that based off a 3 neuron network, and what that is 3 neuron cells. These are the terminal buttons of cell A. This is an entire neuron in cell B, and these are the dendrites of cell C. The entire cells look like this, but I'm just going to concentrate on these 2 parts for cell A and cell C. So again, here's a 3 neuron network, and basically what I have here is that the terminal buttons act as the sending part of the neuron, and the dendrites will act as the receiving part. So, so located in the terminal button, here's just a zoom in of a terminal button. Located in the terminal button, which is in the axon, at the end of an axon, there are particles called synaptic vesicles. And the synaptic vesicles hold neurotransmitters. So what the synaptic vesicles do is they come down and they will bind to what is called the presynaptic membrane. Presynaptic membrane is the membrane of the terminal button. They come down, they bind to the presynaptic membrane, and this causes the release of neurotransmitters into the open space, which is called the synapse. These neurotransmitters right here have a specific shape which will bind to what is called the ionotropic receptor. In a key and lock fashion, just like a key opens the door, this matches the shape of the receptor, and this will open an ionic channel. This is now open once it binds. And now we are inside the membrane of the postsynaptic. This is the postsynaptic membrane, is what the receptors are located on. Okay, so we got synaptic vesicles binding to the presynaptic membrane, which triggers the release of neurotransmitters into the synapse. And once the neurotransmitters bind to the ionotropic receptor, this opens a channel which will allow the movement of 3 different ions into the cell. These 3 different ions are sodium, potassium, and calcium. Once the ionotropic receptor opens up the channel, once the neurotransmitters open up the channel, sodium in the interstitial fluid will begin to start moving down into the channel inside of the membrane. So this is the movement of sodium inside the membrane, because initially sodium is highly concentrated on the outside of the cell and lowly concentrated on the inside. So there's a positive charge and a negative charge, and the negative charge attracts the positive charge, and it begins to flow inside the cell. There is an instrument that measures the flow of these ions into the cell, and it is called an oscilloscope. And before the ion channel opens, the cell is at rest. And on the oscilloscope, with the cell being at rest, that is measured at -70 millivolts. That's the cell at rest before the receptor opens. Once that flow of sodium begins to come in, it makes a movement on the oscilloscope scale, and this movement is called EPSP, which stands for excitatory postsynaptic potential. Again, what that is that sodium flowing into the cell causes a short bump of depolarization, and it makes a little bump on the scale right there. So this is EPSP right here, which is again the flow of sodium into the postsynaptic membrane. So sodium keeps flowing into the cell, and eventually a bunch of EPSPs begin to build up. And that is called the threshold of excitation, threshold of excitation, this buildup of EPSPs is called summation. This is summation. And once summation reaches -65 millivolts, this is where we reach the threshold of excitation. Once it reaches -65 millivolts, it's the necessary charge to open voltage-gated channels, and this initiates more sodium, which causes action potential to begin. So now action potential is taking place, and it's going to shoot up right here up to positive 55 millivolts. So the flow of sodium causes this action potential to happen. Action potential. At this level of millivolts, sodium channels will now close, because sodium has reached its equilibrium on the inside of the postsynaptic membrane. Sodium channel closes. And now, what will take place is that potassium channels will start to open, because potassium is also on the inside of the postsynaptic membrane, and they need to reach equilibrium, which they are not. So here at the peak, sodium channels close because sodium is at its equilibrium, and this now brings it down with the flow of potassium into the cell to a point of hyperpolarization. And what is happening here is that now that potassium is also on the inside. Potassium is leaving the cell. So now we have the flow of sodium in and potassium out. And what this does is, initially when potassium leaves the cell, again, it causes hyperpolarization, which is a decrease on the oscilloscope. So now we have the initiation of a sodium-potassium pump, which basically pumps sodium outside of the cell because sodium has a high concentration on the inside and it's trying to get to equilibrium, and so is potassium. So you have a sodium-potassium pump pumping sodium out and potassium in to bring the cell membrane back at rest, which is a negative 70 millivolts. And at this hyperpolarization, potassium pumps